So the way that you compute the clock period for a pipeline data path is to look for the longest path within any given stage, so between the register file and any pipeline register, as well as between pipeline registers. And since there's one data element between each pipeline stage, we're basically going to take the max of all of those data paths. And so in the instruction fetch stage, we're just going through the instruction memory. So that says takes 2 nanoseconds. In the decode stage, we're just going through the register file. That's 1 nanosecond. In the EX stage, we have to get through the ALU, which is 1.25 nanoseconds. In the MEM stage, again, it's going through a memory, and so that takes 2 nanoseconds. And in the write back stage, again, we're accessing the register file, which is 1 nanosecond. And so the max of all of those values is 2 nanoseconds. And so that's going to be what sets our clock period. In part B, it said, what if we split those memories, because they're so slow, into 2 pieces? And we balanced it evenly so that each of those stages was half of the time to access the memory. And so as a result, each of these pieces would be taking 1 nanosecond. So that changes our equation above. Now we're taking the max of these 2 1 nanosecond IF stages, the 1 nanosecond ID stage, a 1.25 nanosecond EX stage. The 2 MEM stages are also 1 nanosecond each, and then the write back stage is 1 nanosecond. And so the max of all those, now it's the EX stage, which is sticking out and causing our clock period to be 1.25 nanoseconds. So even though we've split these memories in half, we aren't able to drop our clock period in half. We can't double the frequency, but we can get quite a bit of the way there. So what impact does this have on data-dependent instructions? Well, the easy case, if we have an add that writes some register followed by another operation, that is going to read that register so that there's a true dependence between these instructions. Well, it turns out this case isn't affected at all. That because the result of that add is available at the EX stage, we have it in time so that we could bypass it to the immediately subsequent instruction, which would just be entering the EX stage the following cycle. So this case is okay. The cases that cause problems are if we have a load which writes V0 followed by some operation that uses V0. Again, we have a true dependence between these instructions. On the original data path, this was a 1 cycle stall. But on the new data path, that value isn't produced until the end of the M2 stage. Now we have 3 cycles between starting that operation and finishing it, which means that when the subsequent instruction tries to start executing, it doesn't have to stall once, which would allow it to start at this time. It has to stall for 2 cycles so that it can bypass that value correctly. So what was originally a 1 cycle stall now becomes a 2 cycle stall. Finally, there's times where this new pipeline would create stalls where the original pipeline didn't have stalls. So imagine the following scenario. We have a load word into V0. We have some instruction in between, I'll call it a no-op, followed by some instruction that consumes the value V0. On the original pipeline, this wouldn't cause a stall because there was an instruction in between the load and the use, but on this new pipeline, because the MEM stage isn't since the value isn't available to the end of M2, now this thing will cause a 1 cycle stall. That for the same reason that the previous case had a 2 cycle stall, just delaying this instruction by 1 means we still have 1 more cycle stall to handle. Part D asks about the impact this pipeline has on flushes due to taken branches. So recall that the branches are resolved in the EX stage, and because of that, on the original pipeline, we would have a branch instruction, and if we predicted it not taken and it was taken, because it was predicted not taken, there would be 2 cycles worth of instructions that were fetched after the branch, because we wouldn't be resolving the branch until the end of the EX stage. And so we would fetch 2 instructions after the branch before realizing that we should have fetched the target instruction, and that would happen in this 4th cycle. And so we would flush 2 instructions out of the pipeline. Well, because we've extended the front of the pipeline, basically we're going to add 1 more instruction. So in the same way, IF1, IF2, ID, EX. Again, we're still resolving branches at the end of EX, but in the meantime, we're going to predict not taken. So we're going to have 3 subsequent instructions that are going to start executing in the time it takes us to resolve the branch. That only at this time do we know where we're going, and we can say, oh no, really this whole time we should have been fetching the target. And so we're going to have 3 instructions in our pipeline that need to be flushed. So basically it's going to extend the taken branch penalty 1 cycle on this machine. And so this is what the case I've shown for conditional branches, but this is also going to be true for unconditional branches. So even if we resolve unconditional branches like jumps in the ID stage, we still need to fetch them in order to know that they're a taken branch, and so that's going to mean 1 additional cycle. So in the 5-stage pipeline, a jump had 1 flush, now it's going to have 2 flushes. So the final part of this question says, how much faster or slower is the new pipeline than the 5-stage pipeline? And so there's 2 components to the speed of running a program. Recall, we have the number of instructions times the CPI times the clock period. Well, the number of instructions is going to stay constant, and we know the change in clock period from the first 2 parts of this question, that we know that originally it was 2 nanoseconds and now it's 1.25 nanoseconds. But we need to find the impact on the CPI. And so in general, our speed up is going to be the time, the original time divided by the new time. So the original CPI is we're going to say it's 1 and times the clock period of 2 nanoseconds. The new CPI is a little more complicated to compute, but if we look at what's given, it says 10% of the time was spent on stalls and 10% of its time was spent on flushes. And so that means 80% of the time was spent on instruction execution. So time that was not stalls and not flushes. And so then we just need to figure out how much time was spent on stalls and flushes. Well, if the only instructions that stall on the 7-stage pipeline were the ones that already stalled on the 5-stage pipeline, that's this case here, in which case we're going to double the stall time. So we know that was 10% of the time, so we can say that that component of the CPI has been doubled. So 2 times 0.1. And then it says for the flushes, half of them result from taken branches, the other half from jumps. So taken branches went from 2 flush cycles to 3 flush cycles, and that's half of the time. So it's now 3 when it used to be 2, so we've added 1/2 of a cycle for 0.5% of the execution time. In the other case, we've doubled that what was, for jumps, what was 1 cycle of flushes is now 2 cycles of flushes. So this together is the relative CPI to the original case. So it's going to take us more cycles, but the clock period is less. And so if we add all these components together, we get 1.175, and if we multiply out 2 nanoseconds divided by 1.175 times 1.25, we get something which is around 1.36. And so it's about 36% faster than it was. So the clock frequency is quite a bit higher. The CPI is also a little higher, but not nearly as much higher as the clock frequency is. So we do get a net bonus.